This will be a presentation on a model of 2010 admissions data from Augustana College in Rock Island, Illinois. This project was completed by Natalie Viscariello, Benjamin Knapper, and Logan Kruse.
Some background information about our data is that it was provided by Kent Barnes, who is the Vice President of Enrollment at Augustana College. The data set had 2,075 students that were accepted back in 2010, and the goal of the model was to predict whether or not a student would enroll based on significant variables.
The data set we were given had several student variables. These are shown here and are split into categorical and numerical. I'm going to explain some of those that aren't as straightforward. Per ethnic is an indicator of whether or not the student identifies as Hispanic. The status variable had three possibilities: if a student enrolled, if a student paid their deposit but didn't end up enrolling, or if a student rejected our offer. This is eventually what we will want to be modeling as our dependent variable. Class and size stand for the high school class ranking and class size. App rating is a general evaluation of their application, and demonstrated interest is a rating assigned by the admissions office. These are shown here. So we have our data set. However, before we can begin modeling, we need to clean our data. We want to improve the data by removing any potential errors and missing values while retaining as many students as possible in our model.
The purpose of data cleaning is to remove the data that is not available from the survey. Some applicants may have not had some of the variables apply to them or chose not to fill out the survey completely. Next, we wanted to remove the empty columns, which we will refer to later. And lastly, we wanted to add variables to our model by transforming the data. The next step in the project is to remove variables. We do this by using the apply function in R. This function tells us how much data is missing from each of the variables. We then identify which variables need to be removed by removing any of the variables that show that they are missing more than 25% of the entries, thus keeping anything that has more than 75% of the entries. Next step was recoding variables. We made a double major variable, which was 1 if they selected one major and 2 if they selected more than one. An undecided variable, which is 0 if they had not decided on a major and 1 if they had. A state variable, which was altered to be 0 if they were out of state and 1 if they were from the state of Illinois or Iowa. And a status variable, which was 0 if the applicant did not enroll and 1 if they enrolled. The final step in the data cleaning is to remove the missing entries. We want to replace the missing numeric variables with either the mean or the median. We can see that the class and size variables both have outliers based on these box plots, so instead of using the mean, we use the median of these values. Finally, we use the NA.omit function in R to remove the remaining NA values. This left us with 90% of our original data and no missing values.
Another method of data cleaning that was explored was taking the in-state variable, and instead of having Iowa and Illinois represent 1, Illinois represented 1 while all other states represented 0. We also did not take any medians, but instead replaced values with only the mean. There are also no undecided or double major variables.
We will continue going through the process of modeling using the initial data cleaning process. The rest of the analysis methods will be nearly identical. However, the models will yield different results, showing the importance of the decisions made in this step.
The next step after our data has been cleaned is to determine which mathematical model we'll be using. We chose to use Logistic because of our dependent variable enrollment. Enrollment is a binary variable with only two levels: the 0 level, where the student didn't enroll, and the 1 level, where the student did enroll. The logistic model controls for this, keeping our variable in between 0 and 1. We then split our data into a test and a train set. The test set represented 20% of our data, and the train set represented 80%. The train set will be used to create our model, and then that model will be used and then compared against our test set, which will tell us the accuracy of our model. Next, we use the step function to determine important variables. The step function is a function in R that works on a model. After we've created our model using the train set, we apply the step function to find significant variables. At the bottom of this slide are the variables that we found to be significant.
One way to test the predictive power of a model is to use the confusion matrix. The confusion matrix is a matrix of events that are the predicted and the actual of our model. The true positives are in the bottom right, and those are the events that the model predicted to be true that were actually true. So the model says that a student will enroll, and they actually did. The true negatives in blue on the upper left are those that were predicted to not enroll, and they did not. The false positives are those that the model predicted that they would enroll, but they did not. And the false negatives are those students that the model predicted would not come, but they actually did enroll. One metric that we're particularly interested in is the model's accuracy. The accuracy is the proportion of the total number of predictions that were correct. So it's defined as the true positives plus the true negatives over the total cases. The confusion matrix is shown below. Our accuracy for this case was found to be 76.77%. Ideally, we would want all our predictions to be correct, so a perfect model would have 100% accuracy. Specificity tells us the number of times our model was correct in saying a student wouldn't come and they actually didn't. It's also called the true negative rate. It's the proportion of true negatives to all the negatives identified by the model. In this case, the model's specificity was 85.87%. Sensitivity, also known as the true positive rate, tells us the number of times that our model was correct in saying that something was positive. It's defined as the proportion of true positives over all the positives that the model predicted. In our case, it's how often the student actually comes when the model says they will. For both specificity and sensitivity, a perfect model would predict 100%. That is, when the model says a student does or does not attend, it will be correct every time, making the ratios 1/1. Our model had 61.67% sensitivity. Compared to the 86% specificity, this tells us that our model does a much better job at saying when a student will not come than it does saying when a student will. We use the confusion matrix to measure the performance of our different models. One way to do this is the ROC curve, which makes use of sensitivity and specificity over the range of cutoff values. Essentially, a cutoff value is the probability at which the model determines that you will come. For example, here, the cutoff value is 0.5, meaning that if you have a probability of attending that is 0.5 or higher, the model says you're coming. As you change this value, you change the predictions, and so you change the confusion matrix.
The ROC curve is simply a visualization of the confusion matrix. The graph you see here is a depiction of sensitivity versus 1 minus specificity. The green line is created by the train set, and the red line is created by the test set. The reason the ROC curve is important in analyzing the validity of our model is because of the area under the curve, or AUC. The graph you see here with the lines drawn in shows what the area under the curve is. You use the area under the curve of the test set to test how good your model is. For our particular situation, the AUC of our model was 0.8317 out of a possible 1.
We have found our model. It's a logistic regression function dependent upon the person's state, ACT score, demonstrated interest, major, and double major. Now that we've found our model and seen its accuracy in the ROC curve, we decided to try to improve it. We wanted to see if interaction terms were significant. Interaction terms are defined as each categorical variable times each numerical variable. We ran the step function as before, and it was determined that ACT times state and demonstrated interest times state were significant. So, in addition to our other significant variables, we now have these interaction terms as well in our model. To compare the models, we looked at sensitivity, specificity, accuracy, and the area under the ROC curve. With the addition of the interaction terms, accuracy and the area under the curve decreased slightly. Sensitivity increased while specificity decreased. This means that our model, including interaction terms, is better at detecting who will actually come, but overestimates the number of people that will reject the offer. Ultimately, we decided that we wanted to use the accuracy and the AUC to judge the models, so the model without the interaction terms was used.
After determining the best model we can create, we altered the cutoff value to see at what cutoff our model was most accurate. By changing the cutoff value, we change the way that our predictions are arranged in the confusion matrix. This table shows how changing the cutoff affects the accuracy of the model. The following table shows how each variable affects the predictions of our model. The estimate is the beta value of the variables, and the p-value is the significance of the variables. All of these variables are significant by the steps we ran earlier. It is worth noting that, because we are doing a logistic regression model, the estimates showed the amount each variable affects the log odds of an applicant's enrollment. This value can easily be converted to find the odds and probability of enrollment. This is an example of how we interpret numerical variables, such as ACT score. Our beta estimate was negative 0.12054. This means, holding all other predictors constant, one additional point on the ACT decreases the log odds of enrolling by about 0.121. Using the displayed conversion, we can see that this means an additional point on the ACT decreases the odds of enrolling by about 11%. The following is an example of how we interpret our state variable, which is one of our categorical variables. Our reference level was 0, which means that the applicant was in state. All other values within the category are compared with this reference level. For the state variable, the only other category was 1 for out of state. Our beta estimate was 0.70076. This means that, while holding all other variables constant, the log odds for an applicant from out of state increase by about 0.701 compared to the log odds of an applicant from in state. Again, we can convert this to find the odds ratio for the state variable is about 2.015.
The undecided and in-state variables went against our expectations. In encoding in-state as in Illinois, Iowa versus elsewhere, we assumed that people would be more willing to attend because it's the right distance from home, or they'd take advantage of financial aid opportunities for being in-state if they were from Illinois. Instead, we found that the log odds of someone from these two states enrolling is significantly less than outside. This may be attributed to the fact that students from farther away were looking at Augustana or places like it specifically, and so were more likely to enroll if they were accepted. It was thought from our experiences and discussions with classmates that being able to not declare a major or being undecided would increase a student's willingness to enroll. Instead, the undecided major was not significant in predicting someone's log odds of attending. However, we only checked major 1 for an undecided answer. This may be affected by someone feeling the need to provide an answer, so we could have checked answers to majors 2 and 3 for undecided to tell us if a student was sure or not. Something that may have improved our model would be some sort of indication of a student's financial aid package. Many students' decisions may have been affected by this. Some of the limitations of this survey are that it assumes a student's honest answer and that they have a defined gender or racial identity. One potential problem with this is that if a half Asian or half white student, one may check white as race 1 while another may check Asian as race 1, and they would not be considered in the same way. This only included one class of accepted students, so the sample size could have been greater. In addition, it was found that when we split our data into testing and training sets, the model could be changed slightly depending on which subset of students were chosen for the training set. In conclusion, we used a logistic model to find the log odds of someone enrolling at Augustana College given their acceptance. We found that the significant predictors for this were the student's ACT score, their demonstrated interest, their choice of major, and their state.
Using different variables yielded different results, as seen here in our alternate conclusions. We had that the positive indicators of a student enrolling to Augustana were in-state, English creative writing, pre-dentistry, pre-veterinary, app rating, and demonstrated interest. Our negative indicators were the pre-nursing program, pre-law program, secondary education program, ACT score, and the interaction term between in-state and demonstrated interest.
When we look at how these compare, they generally agree. The biggest difference is in the state as a predictor. When you look at state as Illinois versus anywhere else, you get that an Illinois resident is more likely to come. However, when we include Iowa as in-state, the model shows that a person from anywhere else is more likely to come. We can conclude that the students from Iowa are less likely to come if they're accepted. One reason we may have differences is in the selection of our training data set. Although we used 80% of the entries to generate the model, these may have been selected differently between them. The source of difference in this model most likely comes from our data cleaning. We coded our state variables differently, as well as replacing missing values in a different way.
We would like to thank Quick R, located at www.statmethods.net, an introduction to R, which was created by D.M. Smith, and Dr. Ming Zhang for helping us on this project. Thank you.